Hello, this is Project Team 19066, presenting our machine vision systems for car wash applications, sponsored by Mr. Car Wash. The goal of every car wash is to achieve a clean, dry, and shiny car. Comparing these two images, we can see the difference in how the water interacts with the surfaces that have been washed with different washing agents. These properties greatly affect how clean and dry the car gets. Therefore, the car wash can be improved by analyzing the water droplets. To help meet the goal of a clean, dry, and shiny car, two systems have been created. The first system designed by the team is the Droplet and Reflectance system, also referred to as the DRS. This is an in-lab system that is used to analyze a sample coupon that has been washed with the washing agents. The system determines the number of water droplets on the sample coupon, the size of the water droplets, and the RGB values of the sample. These numerical outputs aid the chemical specialist in analyzing the effects of their washing agents so that improvements can be made to the chemical compositions. The second system is the mirror location system, also referred to as the MLS. This is an in-wash system that determines the side view mirror locations. With the location of the mirrors known, the dryers can be set up to better dry the mirrors, as the mirrors are often left with a large amount of water due to their orientation on the vehicle.
Here are the system requirements for both the DRS and the MLS. The most important system requirements in our eyes were the quantity analysis, size analysis, RGB, and the mirror location. Here's our analysis prediction summary. As you can see, all requirements are met or exceeded with margins. For these analysis slides, feel free to pause if you want to look at any details. First is our camera's optical limit, which we use the Johnson criteria in order to have a conservative estimate for identification of the water droplets. Next is our lens's spatial resolution, which we need to be smaller than the resolution of our camera. Next is a geometrical model in order to figure out the FOV of our lens in the object space. Here's some illumination prototyping with different surfaces. Notice the difference between a specular and Lambertian source.
The design for the DRS features a Thorlab scientific camera and 12mm fixed focal length lens that were determined to meet our needs to the analysis shown earlier. The DRS works using a Python algorithm that we created as well as using the supplied Thorlab software. The design includes a rack and pinion focusing mechanism that allows for 105mm of height adjustment. The system is capable of capturing an image and analyzing that image to determine the number of water droplets, the diameter of the water droplets, and the RGB values.
This is our MLS design. This design is intended to locate the passenger side view mirror on the cars as they go through the tunnel of the car wash. We will be using a 2D LiDAR sensor. This sensor has a 0.05 to 10 meter working range with a 270-degree aperture angle. This creates a vertical laser field. This helps solve the problem that the car wash came to us with. They knew the driver's side wheel based on the wheel track within the tunnel, but every car has a different height and width. So this allows us to capture data for any car that goes through the tunnel. This sensor has a 0.33 degree angular resolution. Initially we were concerned with the depth error, but after consulting with SICK, we determined that at 1 meter of working distance, the resolution would be 5.76 millimeters, with a safety factor of 2, which equates to 11.52 millimeters. You can see the calculations for 2 meters of working distance. We believe that every car will be within 1 to 2 meters from the sensor. This sensor outputs XYZ coordinate measurements. We will then take this data and run it through our algorithm that we create to analyze where the closest point is to the sensor. This point is in turn the location of the side view mirror. This is our requirement verification table. I'm not going to go through every one, but I want to highlight a few important ones. Our second verification is the performance requirements. These were not able to be met as due to the coronavirus, none of our materials that are necessary to complete our build are available to us, and the car wash did not want to spend any extra money that they didn't have to. The third requirement is the RGB data that the scientific camera can provide. We have tested this, it works, and so it passes the verification. For the MLS, the mirror location should be done on best effort. Unfortunately, also due to the coronavirus, we were unable to get the parts in time. We were planning on setting up the entire system and hopefully making sure that it works.
This is a result of our droplet detecting algorithm. It outputs a picture with detected droplets, the number of droplets, and their minimum, maximum, and mean radius. It will also save all radius to the computer in .dat format. This is a snapshot of the GUI for DRS. It can be downloaded as a desktop application, so it is pretty user-friendly. I will show what it can do later. This is a snapshot of the GUI for MLS. It is meant to work with the SICK LiDAR software to make measurements, calculate distances, and save all the information for further analysis. We don't have access to the hardware due to the COVID-19 situation, so GUI functionalities related to hardware have not been fully implemented. We have communicated with our sponsor and they're okay with it so long as we provide guidelines on what they should do to build the full system. This is our light source. The distance between the ring light and the wall is approximately 400 millimeters to simulate what it should look like in our system. As you can see, the light source lights up the droplets pretty well. The lighting effect across the whole image is uniform and the droplets stand out from the background. This is the setup of our system. The focuser should be mounted to the base in the mounting system. The blue trackpad is simulating the sample coupon. This is the current LiDAR system. The two pictures on the left represent the setup of the system as it must be on its side to create a vertical field for objects to pass through. We don't have access to any of these parts right now, and other parts have either not been manufactured or delivered, so unfortunately we cannot assemble our hardware to show a complete system. This is the output of the ThorLab software. Displayed is the RGB test data. This data can be extracted and used in our own algorithm to find the pixel peak length for each color and location. Now I will demonstrate some of the functionalities of the GUI. As you can see, the GUI is already open. There is a small symbol for Mr. Car Wash displayed down here. The status area shows the status of the system. Ready means it is ready to take the picture, and busy means it is running the system. To begin with, the user will enter the working distance and hit start. The camera adjust can be used to open the camera API. The snap picture button is used to take the picture. The picture will be saved in the folder called Mr. and displayed here on the GUI. This is the Mr. file. The picture used here is a simple picture taken beforehand. Then the user will hit the detecting button to run the algorithm. This is a detected picture and this is the histogram. We can now hit any button to exit. Now the user can hit the histogram button to have it displayed on the GUI. By clicking on the data file, it will display the calculated results in the text boxes. The Save button should allow the user to save results to SQLite with the option of entering the washing detergent name for future analysis.
This is our Design Day poster. It highlights our sponsor, mentor, and our team members. We have gone through a quick introduction and problem description, materials and methods, and explain our results, along with our conclusions and supporting materials and references.
Here we have the list of all the deliverables along with the format type and delivery date. We will now go over the surprises and lessons learned. Initially, we had a large scope which made the overall project very difficult to manage. However, the team was able to successfully redefine the scope. We reinforced communication skills with sponsor, mentor, and within team members. The second point listed is that we were able to understand the importance of requirements and design process early on the project, which helped to have a more defined purpose and project.
Finally, we just wanted to thank a few people, including Gary Redford, our mentor, Mr. Car Wash, and William Blair from Mr. Car Wash, Thor Labs, and Alex Gilbum from SICK